on the schedule, which is great. So next we're going to hear from Mark Magee, who is a postdoc at the Institute of Cosmology and Gravitation at the University of Portsmouth, working on trying to find lens supernovae. Mark, whenever you're ready.
Thank you. Okay, so first let me start off by saying thanks to the organizers for giving me the opportunity to tell you about my work. So today I'm going to tell you about gravitational lens supernovae and some of our efforts to try and find them in ZTF public data. Okay, so I'll start off by going over some background. So if you're paying attention this morning, a lot of this will be quite familiar. And then I'll move on to talking about the sample that we're using. So again, this is coming from ZTF public data. And based on simulations, we expect that there should be at least one discoverable lens supernova within this sample every year. And then I'll move on to talking about the identification methods that we're using to try and find lens supernovae. So with this work, we really wanted to test these methods on real data. These are published in the literature, and we want to test them on real data and see, can we find any lens supernovae with them? And also, what are the contaminants that we would get so that we know going forward for LSST. And then I'll summarize everything at the end and talk about some future work. So I also want to point out that this is still a work in progress, but if anyone wants to talk about any of this in more detail, I'd be very happy to do that as well. So start off with the background. So again, just to recap, strong gravitational lensing is what happens when you have a background source that's sufficiently well aligned with a massive foreground galaxy, such that you get multiple images of the CM source being formed. You can see that in this image on the left, where we have a supernova in the background, and we have multiple images of that supernova being formed for the observer. So each of these images will take a different path towards us, the observer, and with that, they can also arrive at different times. We can see the impact of that in this figure on the right. So each one of these light curves correspond to one of these different light rays from the image on the left. You can see they have different relative offsets on the x-axis, so they have different time delays. Now, these time delays are sensitive to the path that those rays have taken towards us, and we can use those time delays to measure H0 and do cosmology like we heard about earlier. So finding lens supernovae should be pretty easy, right? We just look for any system in which we see multiple images of the same supernova, and that's it, we're done. But not quite, because nothing's ever so easy. So most of the systems will not be resolvable. So instead, we will not see 4 nice images like we see here. So this is a high resolution image of the system from 16 GEU, UBAR 2017. And you can see we have the lensing galaxy in the center, and then we have multiple images of the background host galaxy being formed. And this is what it looks like with a low resolution image, similar to what we'll have for future for LSST, or sorry, for ZTF, and we'll also have lower resolution for LSST forward as well. So you can see we can't pick out those individual images, we just get one unresolved image. And of course, each of these, I don't know what happened, I pressed the wrong button. Oh, I've messed it up. I'm not that good at dancing. Yes. Okay, cool. Thank you. So where was I? Yes. So we'll not see these different images. We'll get one unresolved one. And again, each of these ones in the high resolution can have a different magnification, different time delays. So it will not necessarily be as easy as just looking for a normal supernova that appears highly magnified. With the unresolved image, it can get a bit more complicated. So hopefully that gives you an idea of why we're interested in finding lens supernovae and some of the challenges related to that as well. So now I will move on and talk about the sample that we're using. So again, we wanted to test this on real data and see can we find any lens supernovae. So we're using the ZTF public survey. I'm sure everyone is familiar with ZTF, but it operates multiple surveys, public, partnership, and Caltech surveys as well. Here, again, we want to test this for going forward. So we're only using stuff that was available at the time from public surveys. So the data that we're using is coming from the brokers. So we started by searching TNS for all publicly announced transients that were observed by ZTF, which was about 28,000 objects between beginning of operations March 2018 down to December last year. And only about 4,000 of them had been spectroscopically classified. And then we did some cross-matching to remove AGN and CVs, so that got rid of a couple thousand objects. And then we placed various cuts on the quality of the light curve and the presence of a host galaxy. So we're going to eventually want to fit the transients with models and estimate colors. So we wanted to make sure that we had good light curves to do that. So we threw away any objects that didn't have at least 4 detections in both the G and R bands. And those detections had to span a period of at least 7 days in each band. And then obviously for it to be a lens galaxy, we need a relatively massive galaxy nearby to act as the lens. So if anything looked like it didn't have a host galaxy, then we got rid of that as well. So we searched for pan stars for each of the objects in the sample and threw away anything that didn't have a host nearby. And that left us with about 12,000 objects to look through for lens supernovae. So now let's move on to the identification methods that we use to try and find them. So the first one is presented in this paper in Quimby 2014. And the idea is to look for very red objects. So lens supernovae should be at high redshift. And that means that most of the flux in the optical blue bands has been shifted to longer wavelengths. So the observer frame colors should be very red. But if it is lens, then it could also be magnified. So it would be much brighter than a normal supernova at that redshift. So if we look for something that's relatively bright, but also extremely red, then we can use that to try and identify lens supernovae. That's demonstrated in this plot from Quimby, where the blue and red shaded regions show simulations of unlensed 1A and core collapse supernovae. And the black line shows the limit for their colors. And then all the symbols here show simulations of lens supernovae. So you can see there are a number of them that are above this black line, indicating that they're much redder than a supernova would be for that magnitude. But you can also see that there are a lot of objects below this black line, so there are a lot of lens supernovae we will miss if we just rely on their colors. But in any case, we wanted to check for objects with very red colors. So we fit the light curves of each of the objects in our sample with Gaussian processes, estimate the color, and put them on a plot like this for the ZTF bands. And with that, we found about 400 objects that had very red colors. So most of them turned out to be AGN, and after a quick visual inspection, threw out the AGN, and that left us with about 60 objects. And then for the remaining 60, we checked whether they were consistent with normal unlensed supernovae, and we found that they were all consistent with various types of supernovae that were just extremely red. So these are 2 examples. So on the left, this is type 1A supernova. You can see it has a C of about 0.9, and C in the SALT model is a combination of the intrinsic color of the supernova and the host extinction. A typical cut you might use in cosmology would be maybe 0.3, but here we've got a very red one. It's not unheard of, just it's very red. And the other parameters you can see are also within the range of what you expect for a normal type 1A supernova and consistent with the redshift of the host galaxy. On the right here, this is now a model, an object compared to a 1B template. Again, you can see it's consistent with the redshift, but also with some host extinction as well. So we started with about 12,000, eventually brought it down to 60, and so far none of them look like they're presenting any compelling evidence for being lens supernovae. But again, this is still a work in progress, and we're still going through the objects to see the most likely types for all of them, the range of reddenings and things like that as well. Okay, so then the next method we used was looking for outliers compared to model fits. This is presented in a series of papers from Goldstein. And the idea here is that we know that most of the lenses we find are massive elliptical galaxies. And we know that most of the supernovae that occur in ellipticals are type 1a supernovae. So if we look for anything that goes off in an elliptical, check whether it's consistent with being a 1a at that redshift. If it's not, then it could be a lens supernova. So this is demonstrated in this figure from Goldstein. So the points here show simulated data points of a lens supernova in the LSST bands. And then the lines show fits assuming the redshift of the lens galaxy. And you can see that it does a very bad job of fitting the redder bands, and that's because it's a higher redshift in respect, so it's much brighter in those bands. So if we monitor all the ellipticals and we check whether there are any, objects in those ellipticals are consistent with not being type 1As, then it could be that they're on supernovae. So for our purposes, we used a combination of the UV, optical, and infrared colors to pick out the ellipticals, and we find about 1,000 objects that look like they had elliptical hosts. And then we fit all of their light curves using salt with the redshift of that elliptical to check whether there are any outliers similar to what you see here. And from that, we found about 200 objects that had outliers. And again, a lot of them were AGN. So we went through and visually inspected them and threw away the AGN, which cut the sample in about half. And then the remaining 2/3 were mostly consistent with type 1As. So the reason they were flagged was usually just because they had some kind of jump detection, like this one you can see on the left. So this is normal type 1A supernova that's well matched by the redshift of the host galaxy, the elliptical. But it just had this jump detection about 150 days after peak, and that caused it to be flagged as an outlier. So we could do some rejection on outliers for the light curves themselves to get rid of these sorts of cases, but again, if we want to do this in real time, and you imagine we had an outlier over here, we wouldn't necessarily be easily able to reject those kinds of cases without the full light curve. We also find a lot of objects that were just not type 1As. So we know that our elliptical selection is not 100% pure. There will be some spirals that make it in. And we also know that there will be a small amount of non-1As that happen in ellipticals. And this is one of them compared to another template, but again, you can see it's consistent with the post redshift. So again, we started with about 12,000 objects, and we find about 1,000 in ellipticals, and then a couple of hundred that had outliers, but so far, none of them presented any compelling evidence to be inconsistent with the redshift of the host galaxy. So those are the different methods that we've tried, and there are a couple of sources of contamination, AGN being the most prominent, and we're playing around with different ways of getting rid of the AGN, looking at the colors and the light curve evolution. Also, we had these spurious detections like this. Again, we can do some kind of rejection to get rid of them. But what we also find is that we can't really rely on, say, the real bogus scores. So say in this exact case, this one had a pretty high score indicating it was real. So we wouldn't be able to reject it in that case. And we also found a lot of objects that had complete light curves where almost all of the points had a very low score, indicating they were bogus, but it was very clearly a real supernova. And since the lens supernovae are so rare, we don't want to throw away any cases like that. And then we also had contaminants for us, which were just non-type 1As, but interesting for other reasons. And then the final source of contamination I want to talk about are sibling supernovae. The siblings are what happen when you have two supernovae that occur in the same galaxy. And in some cases, they also occur sufficiently close together that they can be tagged as the same object. And that's what happened in this case. So here we have two very clear light curves, and they're separated by a little over 2 years. And they're also separated in space by about 0.6 arc seconds. So they were tagged as being one object here. So the siblings are also a really good analog for lens supernovae, because in a lens supernovae, you might have two images of the same source separated by, by a few arc seconds or by a few fractions of an arc second, and by some time delay. That's not entirely unlike two supernovae in the same galaxy. It just happened to occur some time apart. So I should say that this is probably not a lens supernova. This is almost like just two normal supernovae. The first one here was classified spectroscopically as a 1A, with a redshift of 0.1, consistent with the post redshift. The other one was not classified, but it was also consistent being a 1A at the same redshift. So these are not lens, just two supernovae that happen to occur close together in space and time. But again, that makes them good analogs for lens supernovae, given the similarities. You could also imagine a case where maybe some of the parameters here are very similar to each other, maybe except the C value. So it would look like maybe two images of the same supernova together. So we also want to then find as many siblings as possible. So to do this, we use an iterative method of fitting the light curve to check whether they're consistent with having more than one transient for a single object. We find maybe half a dozen cases like this that seem to have at least two light curves. At the minute, this was just using salt, so there could be other cases, where you have, two core paps supernovae or whatever together. So there could be more of them in ZTF, but we found maybe half a dozen. I think only one of them had been published as a sibling pair. So before I wrap up, and then I just wanted to touch on the main limitations of what we found. So again, this is in progress, but this is what we've encountered so far, and the things that we should think about going forward in ZTF and LSST. So the first is that the color cuts, if we look for only very red objects, we're only sensitive to supernovae with high magnifications. Again, you can see in this plot, there are many objects below this black line that we would miss because they're not bright enough for us to see, or they're not so red for that brightness for us to pick out. Another limitation is that we have incomplete elliptical selection. So when I mentioned before that there should be one lens supernova in the public data per year, that was assuming that we could identify all the ellipticals. So far for this, we know that our selection is only about 75% complete. So there's a balance between how many contaminants you want to let in spiral galaxies and how many you're prepared to throw away. But we're also testing other methods of identifying the ellipticals as well. And then the final limitation is that in some cases, it will just not be possible to pick out a supernova as being at the wrong redshift. So to demonstrate this, this is the same figure I showed before from Goldstein. In simulations of a lens supernova being fit with the wrong redshift, and this is what it looks like if you fit it with the correct redshift. So you can see it does a much better job of fitting all the bands, and also has a very high peak magnitude because it's being magnified. But for the ZTF public data, we've only got two bands to work with. We've only got the G and R bands, and that will limit our ability to pick out lens supernovae. So to simulate this, this is that same object fit with only the LSST R and I bands, and fit with the incorrect redshift, which is 0.6. And you see that although the redshift is off by a factor of 2, you can still get a good match with just those bands. So this is probably an extreme example, and to demonstrate some of the limitations doing this for ZTF public data. But you can also imagine, depending on the redshift of the lens and the host galaxy, and just the magnification and properties of the supernova, there will be cases where you can get a good match even with the wrong redshift, and therefore you'll never know there was actually a lens supernova if you just rely on something like this. Okay, so then just to summarize everything, so we looked for lens supernovae in the ZTF public data and started with about 12,000 objects. And we looked for objects that had very red colors. We found a few hundred candidates, but most of them were AGN. And then we had a lot of supernovae that just had been heavily reddened. We looked for supernovae in ellipticals and checked whether they're consistent with being type 1As at that redshift. And again, we found a lot of AGN and some non-1As and a lot of 1As that had junk detections that flagged them as outliers. So the main sources of contamination were then AGN, spurious detections, non-1As, and also sibling supernovae, which are good analogs for lens supernovae. Although the siblings are probably more extreme, you wouldn't expect to actually find many lens supernovae with time delays of the order of 2 years. So some of the stuff we're still working on is refining the selection cuts for ellipticals, for the colors, things like that. Then also testing this in real time. So obviously what I've been showing you has been using the complete light curves for all the objects. But if we do want to do this going forward and treat it as a dry run, then how many contaminants would we get per night if we only use the data available to us at that time? And what would that do to the numbers? Are there many that we could eyeball, or would it be too much, that sort of thing? So that's the end of my talk. Thank you for listening. Take any questions.
Questions for Mark?
With your sibling supernova, what about those light curves made you decide it was sibling and not actually a real lens?
Because they're both consistent with being at the redshift of the galaxy nearby, and one of them was spectroscopically classified as being at that redshift.
Oh, okay.
Also, the colors are slightly different. So like the X1 values, you could, with the uncertainties, they are consistent with being the same, but the colors are a bit off. I imagine you could, but I don't know how much of a change it would be.
Okay, let's see, Justin.
Yeah, just to add to that last bit, is all microlensing could do that too. That chromatic variation. In the earlier one where you had, I think you had like a 1A on one side and a core collapse on one side, and you said that they were red but consistent still with the population parameters. But I noticed, the 1A C value was like 1 or something, which is like consistent but ridiculously red. So what is your threshold for like too red or not too red, I guess?
Well, we haven't. Well, so the threshold to pick them out is basically just if they're above this black line, translated into the ZTF band. So that's how we would pick it out as being red. For this one specifically, the reason that I would throw this one away is because it's still consistent with the redshift. So if it was at a very high redshift, then the secondary maximum would probably be shifted out of the R band and we wouldn't see it. But this just looks like a normal supernova at a low redshift. The peak magnitude is also consistent redshift as well. So again, like I said, we could get a fit with the incorrect redshift and not be able to
Might be a little bit
possible
short
that's
on time
going
with all
on.
the questions.
Thanks. It's really interesting work. Oh, it's not working as it is. Okay, very interesting work. I was wondering if some of the AGN as contamination, if those could also be lensed quasars?
Possibly. We didn't look at them in any more detail. So most of the times the AGN for the colors specifically were just thrown up because the Gaussian processes we're using to fit their light curves didn't work very well. So it's not that they are actually very red. It's just that the model didn't pick them out. But for our purposes, we were just trying to get rid of them. So we didn't look at them anymore.
And then the one on the chat was, how do you decide what's an AGN?
Sorry, say that again?
How do you decide what's an AGN for contamination?
Oh, it's done visually. When you look at the light curves, you can see if it lasts a really long time, if it has a lot of detections over years, then probably an AGN and not supernova.
Got it. Okay. I think there's one more on Zoom.
Yeah, I had a bit of a more technical question. If you might tell me a little more about the GP interpolation you used, maybe any challenges you encountered to like take that versus maybe a more physically motivated model?
So for the Gaussian processes, we just threw them into George.
Okay.
And that's why I think probably the AGN were, like the AGN light curves look very different from the normal 1A light curves.
Yeah.
And that's why it would fail on them. So it really was just a simple stick them in there and do the bits.
And you find that it works. Good.
And then we might have to switch our AV because I think the person, let's see, somebody's hand was raised on here. Is that right?
Yeah. So can you hear me?
Yes.
Yeah. So excellent talk. So I was asking for this sibling supernovae, is it possible after the it is going some field detonation or something, and the same supernova is going the same progenitor is going to explosion again?
Sorry, can you ask the question one more time? We had a little bit of trouble here.
Okay, so this is regarding the sibling supernovae. So is it possible that after the first explosion, like it is a failed detonation or something like that, the same supernova is going to explosion again?
Yep, that's possible. I mean, we do see cases like that. We didn't find any in our sample, but that does happen. Although I think in that case, they probably wouldn't be the same magnitude, so you would easily distinguish them as being different. I mean, it would look just like the same supernova again, say.
Okay, thanks.
In this case, yeah. But if it was a pre-outburst of a supernova, then
Okay, we're short on time, so let's give Mark a round of applause again.